Hello, everybody, and thank you for tuning in to my talk on efficient and simple algorithms for fault-tolerant spanners. My name is Caleb Robelle, and I'm a rising senior at the University of Maryland, Baltimore County. This work was done jointly with my mentor, Dr. Michael Dinitz at Johns Hopkins University. I'll begin with a formal definition of what a spanner is. Let G be a graph with non-negative edge weights. We say that a subgraph G' is a T-spanner of G if distances between all pairs of vertices are preserved up to some multiplicative factor T. This multiplicative factor T is called the stretch of the spanner. Less formally, spanners are a form of graph sparsifiers that approximately preserve distances. For an example, consider the following unweighted graph. The subgraph on the right is a 3-spanner of it, since distances between any pair of vertices are no more than 3 times the shortest path distance between them in the original graph. We can easily construct spanners using the greedy construction algorithm of Althöfer et al., which works as follows. We initialize our spanner by adding all vertices from our original graph, but none of the edges. We then consider edges in non-decreasing order of weight and check if the spanner condition holds for the corresponding pair of vertices. If it holds, we don't add the edge. If it does not hold, we must add the edge. Since we're working in the unweighted setting, I can consider the edges in arbitrary order. For the purposes of this example, I'll first look at the edge between V2 and V1. Currently, there does not exist a path between them, so the distance is infinite. Therefore, we must include this edge. For the same reason, we include the edge between V1 and V3, as well as the edge between V3 and V4. Now, let's consider the edge between V4 and V2. Notice that there already exists a path which is less than or equal to 3 times the distance between V4 and V2 in the original graph. Therefore, we do not include it. Similarly, the edge between V2 and V4 is not included, V2 and V3. A similar data structure of interest to those in the field of distributed computing is the fault-tolerant spanner. Formally, given a graph G, we say that a subgraph G' is an F-vertex fault-tolerant T-spanner of G if we can remove up to F vertices, and what remains of the spanner is a T-spanner of the original graph with those same vertices removed. The idea here is that the spanner is now robust against failure of up to F vertices. Edge fault-tolerant spanners can be defined similarly, but in this talk, I will focus on the vertex fault-tolerant case. For an example, consider the following familiar graph. The subgraph to the right of it is a 1-vertex fault-tolerant 3-spanner of the original graph. Notice that if we remove any one node from both graphs, what remains on the right will still be a 3-spanner of what remains on the left. We can construct vertex fault-tolerant spanners using the greedy construction algorithm of Bodwin et al., which works in a similar way to the greedy construction algorithm of Althöfer. Once again, we initialize our spanner by adding all of the vertices from the original graph, but none of the edges. We then consider each edge in non-decreasing order of weight. For the corresponding pair of vertices, we check if there exists a fault set, not containing them, which breaks the spanner condition for this pair of vertices. If there exists such a fault set, we add the edge. If not, we do not add the edge. Similarly to our previous example, when looking at a graph which is unweighted, we can consider the edges in arbitrary order. For this example, I'll consider them in the same order I did when we were building a non-fault-tolerant spanner. So let's look at the edge between V2 and V1 first. Currently, there does not exist a path between them, so the distance is infinite. So we have to include the edge, just like in our previous example. And just like in our previous example, we include the edge between V1 and V3 as well as the edge between V3 and V4. The first difference becomes apparent when we consider the edge between V2 and V4. Now, when we consider this edge, we notice that if we remove vertex V1 from both graphs, the distance between V2 and V4 in the spanner we've built so far becomes infinite, whereas in the original graph, the distance remains the same. Therefore, we must include this edge in order to make the spanner condition for these vertices robust against vertex failure of up to 1 vertex. Now, when considering the edge between V2 and V3, notice that removing either V1 or V4 does not cause the distance between V2 and V3 to become greater than 3 times the shortest distance between them in the original graph. Therefore, we don't add it. And what we end up with is the following subgraph as our 1-vertex fault-tolerant 3-spanner. In the paper, where they gave the now standard greedy construction algorithm for spanners, Althöfer et al. Also proved the following theorem, which is the sort of fundamental theorem of spanners. They showed that given an arbitrary graph G and an arbitrary natural number K, G will have a 2K minus 1 spanner with big O of n to the 1 plus 1 over K edges. And this bound is tight, assuming the Erdős-Girth conjecture, which is widely believed to be true. They also showed that the greedy algorithm they defined produces spanners of this size. And now that we have a tight bound for spanner size, one might ask the following question, which is, how much will it cost me to add the fault tolerance property? Well, let's take a look at some of the past work in this area. In 2009, Chechik et al. Gave the first spanner construction for general graphs, which had an added cost of f squared k to the f plus 1 log to the 1 minus 1 over k n. 2 years later, Dinitz and Krauthammer gave a construction which had an added cost of f to the 2 minus 1 over k log n. Then, in 2018, Bodwin et al. Provided, in addition to providing the greedy construction algorithm we used earlier, showed that this algorithm produced spanners of optimal size in the case of fixed stretch in the vertex fault-tolerant setting. This upper bound, however, is not known to be tight for edge fault-tolerant spanners for a stretch greater than 5, as they were only able to show a weaker lower bound in that case. The following year, Bodwin and Patel gave a matching upper bound an upper bound which matched the lower bound in the vertex fault-tolerant case by analyzing the same greedy construction algorithm. So this is pretty good. It shows that this greedy construction algorithm they proposed builds spanners which have optimal size. There's only one downside to this algorithm, which is that it takes exponential time in the size of the input graph. Well, this begs the question, is there an algorithm which produces optimal or near optimal? So by near optimal, I mean all optimal in the fault tolerance threshold fault tolerance spanners in polynomial time, to which we reply yes. And we present a polynomial time algorithm which is only which builds spanners that are only a linear factor in k away from optimal in size. So our size bound is big O k f to the 1 minus 1 over k n to the 1 plus 1 over k. And in order to motivate why we wanted to come up with such an algorithm and how we came up with this algorithm, let's first take another look at the greedy construction algorithm of Althöfer. In each iteration of this algorithm, we check if the spanner condition holds for a certain pair of vertices, and this can be done very easily. You simply run your favorite shortest path algorithm on the spanner you've built so far and check if the distance between the two vertices satisfies the spanner property. Now, let's take a look at the greedy vertex fault-tolerant algorithm of Bodwin et al. This algorithm is a very natural extension of the previous one. However, in each iteration, instead of checking if the spanner condition holds for a pair of vertices, we check if the spanner condition for that pair of vertices is robust to failure for a set of up to f vertex failures. However, unlike the previous algorithm, this cannot be done in, it's not known whether or not this can't be done. What I mean to say is this can't be done in polynomial time. In fact, this problem of determining whether or not a fault set exists is an NP-hard one. If we can replace this finding a fault set subroutine with one that runs in polynomial time, then we can run this algorithm in polynomial time, as we'll simply be running a polynomial time algorithm polynomial number of times. So we'll first look at how we might be able to do this in the unweighted case, and then I'll show how we can generalize this approach, our approach to the weighted case. So we first look at this problem called length-bounded cut, which is defined as follows. Given a graph G, two vertices u and v, and a natural number t, we want to find the smallest set of vertices which, when removed from G, break all u, v paths of length less than or equal to t. Independent of being the smallest set which does this, we call any set that does this a length t cut. If we can solve this problem, we claim that we can solve the problem of finding fault sets. And that's because the problem of finding a fault set is equivalent to finding a length 2k minus 1 cut of size less than f. Well, if we can do that, then that means we know whether or not we have to add an edge. But as our luck would have it, LBC is known to be an NP-hard problem. So what we do is we look at a gap decision variant of this problem instead, which we defined as follows. This gap decision problem takes in the same parameters as LBC plus a new parameter alpha, a natural number. It returns yes if there exists a length t cut of size less than or equal to alpha, and it returns no if there exists no length t cuts of size less than or equal to alpha. This is essentially a t approximation for LBC. And in the case where we have the smallest length t cut falling in between alpha and alpha t, we are allowed to return either yes or no. It turns out that this problem can be solved by a very simple algorithm, which we state now. We simply run a breadth-first search to find a UV path of length at most t. If we cannot find a UV path with length less than or equal to t, we return yes. Otherwise, we add all nodes along the path except u and v to our cut and remove them from the graph. If we can do this successfully alpha plus 1 times, then we return no. It's very easy to see that this algorithm will run in time big O n plus n times alpha, as we're going to be running a breadth-first search on our graph alpha times. Before I prove correctness of this algorithm, let me go over some ideas that will make the proofs easier to understand. Consider the optimal or any optimal length t cut for a pair of vertices u and v. We know that every UV path with length less than or equal to t will contain at least one element of opt, and each element of opt will be in at least one of these paths. Now, we consider all of the paths of length less than or equal to t that our algorithm finds between u and v. Since we remove all nodes along each of these paths upon finding them, we know that each of these paths will be node disjoint, with the exception of uv. The algorithm works by removing these paths one by one, alpha plus 1 times, or until we run out of paths, whichever comes first. So if we just look at u and v and the nodes and edges that make up these paths the algorithm finds, we'll see something that looks like this. The nodes I've just circled are the nodes that make up opt. As I mentioned before, there will be at least one in every single one of these paths. Then we remove one of these paths from the graph. We then proceed to do this alpha plus 1 times or until we run out of paths to remove. So with all of this in mind, we're ready to look at a proof of correctness of the algorithm. We're going to have two cases we need to look at. In case 1, we have that opt has at most alpha vertices. In this case, we claim that we run out of path to remove by the end of iteration alpha. Why does this happen? Well, we know that there is at least one node from opt in each UV path of length less than or equal to t. We also know that each of the paths the algorithm finds are node disjoint, with the exception of u and v, of course. So, after at most alpha iterations, we will have removed every single node in opt from the graph. Well, we know that opt is a length t cut, so that means that there are no more UV paths with length less than or equal to t. So in iteration alpha plus 1, we do not find a path between u and v, and the algorithm returns yes. In case 2, we have that opt has greater than alpha t vertices. In this case, we have that at the end of iteration alpha, there will be at least one UV path of length less than or equal to t remaining. This is because in each iteration, we remove at most t vertices from the graph. So by the end of iteration alpha, we've removed at most alpha t vertices from the graph. We know that opt is the smallest length t cut, so the set of vertices we've removed cannot possibly be a length t cut, which means there must be at least one UV path remaining of length less than or equal to t. Therefore, in iteration alpha plus 1, the algorithm will find this path, or one of these paths, remove it, then exit the main loop, at which point it will return no. So now that we've proved correctness of this algorithm, our foray into the land of LBC is finished, and we return back to the original problem of determining if an edge is necessary when constructing a vertex fault-tolerant spanner. So here we have our unweighted vertex fault-tolerant algorithm. We claim that we can use the LBC approximation algorithm to determine if an edge is necessary. Here, we've modified the greedy construction algorithm of Bodwin et al. In the following way. In each iteration, instead of checking if, for a given pair of vertices, the spanner condition is robust against F vertex faults, we run our LBC approximation on the spanner we've constructed so far. When the algorithm returns yes, that indicates that there may exist a fault set of size F, of size less than or equal to F, and we must add this edge. When it returns no, it implies that there does not exist a fault set of size less than or equal to F, and we do not need to add this edge. So in order to prove correctness, we first consider an arbitrary fault set F and an edge with terminals not in F. We must show that if all of these vertices in F fail, the spanner condition is still satisfied by our spanner. For vertices U and V, there are two cases we must consider. In case one, we have that UV is in our spanner. In this case, the spanner condition holds trivially when we remove F from our spanner and the original graph. And this is because U and V are connected by an edge with unit length. In case two, we have that the edge UV is not in our spanner. This means that while we were constructing our spanner, when we asked the LBC approximation algorithm if we should add UV, it said no. This means that there is no length 2k minus 1 cut of size less than or equal to F, meaning that the spanner property holds if we remove all the vertices in our fault set F, since it cannot be a length 2k minus 1 cut of size. It cannot be a length t cut, since the smallest length t cut there is no length t cut of size less than or equal to F. Now that we know this algorithm works, let's try and figure out the size of the spanners it builds. In our paper, we used the analysis of Bodwin and Patel. From a very high level, it looked something like this. We showed that every spanner H that our algorithm produced had a subgraph H prime with high girth and a similar number of edges. Then, since we know that H prime is high girth, we know it can't have too many edges, which means H also cannot have too many edges. Unfortunately, we couldn't use their analysis as a black box, since some of their theorems were specific to the unmodified greedy construction algorithm. For details, you can look at the paper, but what it boiled down to was replacing all instances of F in their analysis with KF, and this is due to our using an approximation algorithm to decide whether or not an edge is necessary. So this takes their size bound and adds a factor of k. So our bound is k, f to the 1 minus 1 over k, n to the 1 plus 1 over k. We now claim that the algorithm has the following running time. The proof of this is actually very straightforward, since we just proved this size bound on the spanner. We know that we run the LBC approximation algorithm with alpha equals f and t equal to 2k minus 1 on h once for each edge in G. Recall that the LBC approximation algorithm has the following running time. Well, now we simply plug in to this running time the parameters alpha. For alpha, we plug in f. For m, we plug in a size bound for our spanner. Then we multiply by m, the number of edges in G, to get our running time. This is great. We now have a polynomial time algorithm for constructing unweighted vertex fault-tolerant spanners with near optimal size. But what can we say about the weighted case? Well, the first thing to consider is whether or not we can blindly apply our solution for the unweighted case to the weighted case. Unfortunately, our LBC approximation algorithm does not work for the weighted case. In fact, it is an open problem to come up with an efficient approximation algorithm for LBC in the weighted case. Fortunately for us, we can simply reduce the weighted case to the unweighted case by considering edges in increasing order of weight. So here we show our weighted fault-tolerant greedy construction algorithm. If you look at the main loop of the algorithm, you can see that we are still using the LBC approximation algorithm to decide whether or not to add an edge, despite my telling you just a second ago that it did not work in the weighted case. What we are actually doing here is running the algorithm on the spanner we've built so far, but ignoring edge weights. Thanks to the way the greedy algorithm works, the edge weights aren't necessary except for in the pre-processing step where we sort them by weight. The proof of correctness for this algorithm looks similar to the proof in the unweighted case, but there are some key differences. Once again, we consider an arbitrary fault set F and an edge UV with terminals not an F. In the first case, we have that UV is added to the spanner when constructing a spanner for G. In this case, we can fail any set of vertices not including UV, and the spanner condition will still be satisfied for the distance between UV in whatever remains of our spanner. This is because they will be connected by an edge. Something to note is that in the weighted case, we assume, without loss of generality, that for any vertices connected by an edge, the shortest path between those vertices will be that edge. In the second case, we have that we did not add UV to the spanner. This means that at the time the algorithm considered UV, the LBC approximation algorithm returned no. What does that mean to us? It means that there was no set of fewer than F vertices, which when removed from H, broke all less than or equal to T hop paths between U and V. This means that we can fail all vertices in F, and there will still be a less than or equal to T hop path between U and V. Note that I said T hop paths and not length T paths, since we are ignoring edge weights after sorting the edges by weight. So our spanner at this time will look something like this, and then we fail this fault set, and we're left with at least a path with less than or equal to T hops between U and V. Since we ran the algorithm, the LBC algorithm, with T equal to 2K minus 1, we know that R will be less than or equal to 2K minus 1. Now we consider the weights of each of these edges. Since they're already a part of our spanner, we know that they must have been considered before the edge UV, which means that their weights are less than or equal to the weight of UV. Taking the sum over their weights yields the following inequality, which then tells us that the spanner condition still holds for U and V after removing F. Well, this is neat. We've just shown that after the initial sorting of edges, we can disregard edge weights and pretend we're constructing an unweighted fault-tolerant spanner. Now that we have an algorithm for constructing spanners in the weighted case, let's take a look at the size of the spanners it creates and how long it takes to build those spanners. Recall that our analysis in the unweighted case worked for arbitrary orderings of edges. And in the weighted case, all we're looking at is a specific ordering of the edges. Therefore, we can simply carry over our size and time bounds with no additional work. So we have that the weighted greedy algorithm produces spanners of the same size and runs in the same time. So in closing, before I end my talk, I'd like to go back over some of the key ideas I introduced. Given a graph G, a spanner is a subgraph that allows us to approximately preserve distances in G. Fault-tolerant spanners have the additional property that this approximation is robust to vertex or edge failure up to some threshold F. We developed a polynomial time algorithm for constructing unweighted fault-tolerant spanners by replacing an exponential time subroutine for finding fault sets with a polynomial time approximation algorithm for length-bounded cut. We then showed that constructing weighted spanners could be reduced to constructing unweighted spanners by considering the edges in non-decreasing order of weight. At the time of submission, an open question that we proposed was removing this linear factor of k from the size of the spanners our algorithm produces, while still having a polytime algorithm. This problem has since been solved by Bodwin, Dinitz, and Robelle, and you can check out our results on arXiv. An additional open question is whether we can improve the size bounds for edge fault-tolerant spanners for stretch greater than or equal to 5. There is currently a gap in the upper and lower bounds, and it would be nice to close it. Once again, thank you for listening.